Is he there?
Just a second, just a second.
Working on it.
So it looks like your recording started.
Cool. So, hi folks, welcome to the April Northwest C++ meeting. Couple of announcements here. Still got a couple of people coming in. Okay. So a couple of announcements here to start. I just want to remind everyone that, as the meeting winds down, if folks want to hang out and just chat after the meeting, you're more than welcome to do so. The meeting room will stay open until the last person leaves, and then it just closes down automatically. So if people want to hang out and chat, just do it. Just because, myself or Robin or whoever seems to be running the meeting looks like they're done and gone, that does not mean you have to leave. The next one is the September meeting this year will be lightning rounds. So 5 to 15-minute presentations for multiple people. If you want to sign up for that, just let me know. And as we get closer, I'll try to get that a little more organized. But September meeting will be lightning rounds. Also, if you want to practice lightning rounds for CPPCon, which will be in October, that would be a really good place to do it. Brett, do you have any updates or comments for CPPCon or CPP Now you want to make?
Well, CPP Now is will be May 2nd through the 7th. It will be virtual, so you don't need to leave your desk. But you will need to be still working at your job, so I'm not just joking. Also, CPPCon will be September 51st or October 21st, whichever you like. It will be a hybrid conference. We're planning in person, or you can attend virtually. There will be probably 5 to 6 tracks of people on site, of presentations on site, and 2 tracks for online. There will be some crossover between the two, but we're trying to make sure that people online on site will get some more information. But if you would like to attend, if you can't attend, or you would just still like to get some information, we would love to have you join online. We also need volunteers for both. We will need a full staff of 60 volunteers on site, and if you are interested, please join us. We also will need volunteers to help with the virtual portion of the conference as well. This year, we will also try to be more engaged with the presenters. The volunteers will try to be more engaged with the presenters on site, so that we have better coordination. So if you're interested, please send me an email to volunteers@cppcon.com. Other than that, I have nothing else.
Probably
Okay.
the domain is cppcon.org.
Sorry, org. Yes. Thanks, Robin.
Okay, with that, we'll turn it over to Walter Bright, and he'll talk about destroying all memory corruption.
Hey, everybody. I'm Walter Bright, and I'm going to talking about destroying all memory corruption. Okay, first off, memory corruption seems to happen all the time. It was just in the news today, if you watch Hacker News and Reddit News. Signal's embroiled with an outfit that snoops on the phone, and they sort of did a reverse hack, taking advantage of probably memory overflow bugs in their forensic software to mess with them. So this is a continual and ongoing problem. it turns out that you can't just look at code and see if it has memory problems. It's really hard to manually review code for it. And then once it is free of memory corruption, anybody can submit a pull request and introduce memory corruption at any time. And it's a really hard thing to head off and prevent. So how many of you people use program in C and C++? And you all know how memory unsafe and susceptible those languages are. And do you really believe that you can have a C-like or C++-like language that can be memory safe? Well, if you don't believe it, I'm going to show you how it can be done. The number one memory corruption problem is always buffer flows. I think it's something like 60, 70% of buffer overflow problems. What happens is you have a buffer, you're writing past the end of it, and if the attacker is providing the malicious data that's to be written past the end of it, you can use that to inject any source code you want into the application and have it run. So memory corruption is buffer overflows is a very common problem and a very bad one. So how does the D programming language end buffer overflows? The first thing it does is it uses something called a dynamic array, sometimes called a slice, instead of just a pointer. And the nice thing about a slice is a pair. One item in the pair is a pointer and the other item is a length. The advantage of that is then you can implement array overflow protection by checking the bounds of the array. And just with this one small improvement to the language, you suddenly eliminate a vast number of memory corruption bugs. The next thing you can do is raw pointers in C are ubiquitous. You can't really do much without using raw pointers. Well, dynamic arrays, first off, take a big slice of those raw pointers and make them unnecessary. The other thing is you take a C++ feature called passing a reference instead of a pointer, and D takes that and goes a little further with that. A ref pointer cannot have its pointer manipulated and its pointer value cannot escape. I'll get into more of that later. Another thing you can do to resist buffer overflows is make extensive use of const and immutable. Const gives you a read-only view of data. If you have a read-only view of the data, then malicious data cannot overwrite it. And immutable data goes even further. Is not only is it a read-only view, but it means no other views can modify it at the same time. So having a pointer to immutable data, a reference to immutable data, or a slice of immutable data is a really robust way to program. The next kind of problem is stack corruption. Stack corruption is when you return from a function and there's a pointer that's still live that's pointing into the expired stack frames. These aren't as common, but they can be very difficult to detect because who knows where pointers are pointing to. You'll often have pointers in the local variables for efficiency's sake, and you want to ensure that those pointers don't get away from you and are not returned from the function. So D has 3 features that conspire together to prevent returning pointers to expired stack frames. The first is passing parameters by reference. And the next one is return. If you pass the parameter by return, it means that it will be returned by the function as part of the return value. And a scope annotation on a parameter means that the pointer you're passing into a function will not escape that function. So it's treated like a pointer into the stack then. And so with the combination of these three things, you can control your pointers to local variables to make sure that they don't escape. And this is all with zero runtime cost. It's strictly a compile time creature. Another way you can get memory corruption is by casting non-pointers to pointers, and you have pointers lying on top of other types like you get with unions. So D disallows these things in code that's marked as safe code. Okay, then the next big category of problems are allocation bugs. And the easy way to remove or not have allocation memory corruption bugs is use a garbage collector. Now I know immediately all you see in the C++ programmers are going to say, I don't want to use the garbage collector. And there are various reasons. Some make sense, some are more tradition, but I'll not argue about whether GC is a good idea. We're going to figure out how to not have memory corruption and not use a GC. So your options when you're not using the GC are an explicit, using malloc and free explicitly, which also include writing your own storage allocator, which is popular in systems programming languages. The next one is resource acquisition is initialization, which means when your data goes out of scope, it calls a destructor and frees itself. And the third option is reference counting. So we'll be going over these. Explicit malloc and free is a traditional C way of allocating and managing memory. And it suffers from 4 distinct problems. The first is you allocate memory and then you never free it. It's called a memory leak. Another thing you do, which is even worse, is using a pointer after you freed it. If you continue to use a pointer after it's been freed, you definitely are going to have memory corruption problems. The next thing is freeing more than once. Some storage allocators have protection against that, but usually they don't. And freeing more than once also results in corrupting, or often results in corrupting the heap or your memory, or you try to free memory that you never allocated in the first place. So all these things get you into trouble. Resource acquisition is initialization, is a natural fit for scoped objects, and C++ has proven that this works very well. The trouble with it is it's not so good for non-scope patterns, like a data structure. Reference counting. Reference counting, languages like Objective-C and COM programming really set a store by reference counting as a way to manage memory without corruption. But it does have one serious problem, which is illustrated by this example. We have a struct S and its payload is a pointer P, and we omit all the ref counting machinery because it's irrelevant to this and it consumes up a lot of lines of code that are distracting. So we just omit that, just assume it's there. And we have a function called main and create an instance of S, initialize the pointer to a pointer that's on to a value that's on the stack, and then call this function. Now this function takes 2 parameters and both are passed by reference. And by passing a ref counted object by reference means you're not incrementing or decrementing the reference count. You're just passing a pointer to it. And the reason for passing parameters this way is for efficiency, because incrementing and decrementing the reference count can be fairly slow. But here's the problem you went into. You have 2 live pointers to S being passed a function, and then we assign a new value to one of them. And what happens when you do assignment to a live object is it frees the previous object before it assigns the new value. So the previous contents of S is destroyed. But wait a minute, T is still a live reference to the previous object that was just destroyed. And if we assign through the pointer to it, we've got instant memory corruption. Okay, how many of you have had this problem with reference counted objects? Oh, I don't see any way in this thing for I can see any hands raised, so I'll just take your word for it that some of you are raising your hand. Or you can yell, by the way, if you have any questions while I'm talking, always just yell out, or is there a chat window on this? I don't see one.
Just in case, I'll mention that you can use your mouse pointer to point to particular parts of the screen to attract attention.
Oh, you can see my mouse pointer?
Yes.
Ah, yes. I'm new with using this software, so. Okay, good. So the issue is having two pointers to the same object, one or both of which is mutable. If you have this sort of thing, you can have memory corruption problems, as is evident here with the reference counted object. So we made a change to D, and here's a link to it, which is if we're calling a function, you can't pass more than one reference to the same memory object to the function's parameters, if any of those references happen to be mutable. And this dealt with some of the problem, but not all of the problem, because you know there are ways to hide what you're passing a reference to. So what we're going to do is generalize then to disallowing more than one reference to the same memory object if any of those references are mutable. Now, does this sound familiar to anyone? Nobody?
No.
I believe you've all heard this before.
Yep.
Okay, it's basically the guiding principle behind Rust. And we can clarify this a little bit more by we'll allow one mutable reference and many const references. And what is not allowed is more than one mutable reference or mixed mutable and const references. And I don't know how to prove that this works, but if you think about it, I can convince myself that it works. I know that may not be very satisfying. You'd want to see proof, but I'm not really sure how to do a proof. But anyhow, it seems to work. Rust has done a very good job of demonstrating to everybody that it works. So what is the concept of ownership? Ownership is a single mutable reference to a memory object is said to own the object. For example, if our function f returns a pointer, we assign it to p. P is now considered the owner of the piece of memory returned by function f. It becomes more interesting if we can transfer ownership, which we can move it to another variable. So it starts off with p being the owner. Now we assign the value of p to q, and p becomes implicitly invalid now. Now q owns it, but if we go back, we can assign through q because q owns it. But if we assign through p, now we get an error because p is invalid. Notice that we're still using normal C, C++, and D syntax. We're not doing anything strange with the syntax here. So instead of transferring, sometimes we'd like to just temporarily borrow a reference. And by borrowing it means we copy it or transfer it to a new variable. We use it for a bit, and then when we're done with it, the ownership goes back to where we copied it from. And how we tell the compiler that we're just borrowing this reference is we put the keyword scope in front of it. And if you'll remember, scope I used earlier for parameters to say that a pointer or a scope parameter does not escape the function it's in, and this idea transfers neatly to scope. You're basically borrowing it from wherever it came from. So we can use it. And now if we start using P again, it implicitly terminates the borrow of B. So if we try to use B after that, we get an error message from the compiler that B is invalid. And I'd like to emphasize in all this that none of these checks are happening at runtime. They're all happening at compile time. So they have zero impact on code generation and runtime performance. Okay, now, if you're used to compilers and all that, you know that this is not an easy thing to accomplish. And how does the compiler know that B is no longer valid? And a borrowed reference ends when one of the following happens. It's the last use of the reference goes out of scope, or the owner is used again. So I know that in some other languages it has to actually go out of scope to not be used, but it turns out that that's really not necessary. We can track the last use of the borrowed reference, and we can track whenever the owner is used again. And referring to when it runs, it's not useful anymore, is we call that the end of its lifetime. And to determine the end of a lifetime of a variable, we use a thing called data flow analysis. Now, who's heard of data flow analysis with a compiler? Usually that's used when you're optimizing code. Using your data flow analysis to do optimizations like copy propagation, constant propagation, dead assignment elimination, dead variable elimination. You use it for allocating variables to registers, use it for loop optimizations, all kinds of things. And it turns out that data flow analysis is ideal for figuring out the lifetimes of variables and ownership of variables. So how we do it is decompose a function structure into a collection of blocks of code collected by edges, and those edges are the paths from one block to another. So all your control structure, your ifs, your whiles, your for loops, your for each loops are all decomposed into block of code and then go to one of these other blocks of code. And that makes it very conducive for analysis. And we construct a data flow equation for every block. And the data flow equation looks like the output equals a transformation of the input. And we wind up with n equations for n unknowns, where n is the number of blocks in the in your control flow graph. And the input and output for this data flow analysis are the states of each of the variables being tracked. Is it dead? Is it live? Is it an owner? Or is it borrowed? So a pointer is created when a function is called that returns a pointer. And it's moved to P as part of the initialization. And this is creating an owning pointer. P is an owner. Pointer destruct is destroyed when it is moved to a function. So here we take our pointer and we move it to function G, which means P is no longer valid and we can no longer use it. Dangling pointer is a live pointer that we didn't do anything with, but it ran out of scope. For example, we take our function, returns a pointer, and then the function, and then it's never used and the function returns, well, the compiler gives you an error saying, hey, what do I do with this pointer? You created it, it's an owner, we can't just abandon it. Functions can also take ownership, and it takes ownership when you pass a pointer to it. So here in function H, we take our owning pointer P and we transfer it to G, no problem, because now it's G's problem. It turns out that G has an error because it doesn't do anything with it and it's dangling, but that is G's problem. And one thing you might want to notice is these functions are annotated with @live, and that annotation is the only syntactical change to D to support this ownership borrowing system. And it says that this function gets the ownership borrow analysis applied to it. That makes it completely compatible with existing code. Now, if we want to borrow pointers, we go back to the scope. We annotate the parameter with scope, because scope says that the parameter cannot escape the function. Well, that's perfect for borrowing. And we take a borrowed pointer B, which is passed to N, and we pass it to M. Well, M borrows it, and then when M is done with it, it returns it, although it doesn't actually return it. It gives up its borrow. And then we can, now the function N owns B again and passes again to G, but G's parameter is not annotated with scope, which means it's a transfer, not a borrow. And then you get a compiler error that says, well, I've borrowed my pointer B, which means I cannot transfer it to someone else. I can only loan it to someone else, but I can't move it to someone else. Okay, so here we have an example of control flow where we have 3 basic blocks that do 3 different things, and those arrows are transfer of control. Now, those arrows might be set off by an if-then statement. And after that control, after the first block is executed, P is valid, and it goes to those other 2 blocks. And on one of those blocks, it transfers it to the function G. And since it transfers P to function G, then P is invalid. And now we're at the bottom block, which has flow analysis coming from 2 previous blocks, one that says P is valid and the other that P is invalid. What do? We give an error. You cannot merge 2 paths where a variable is in a different state, i.e. it cannot be both valid and invalid. So let's rethink these things in terms of malloc and free, which I presented simplified versions of them here, which hopefully, since everybody understands how malloc and free works, it'll show how all these features work. And we'll first note that malloc and free cannot be @live because they're taking a value and destroying it, and the flow analysis or the analysis needs to know how something is destroyed. And so it has to be like a system call or unsafe code, or in D's case, a not @live function. So it doesn't get the checking, so you can do whatever you want with it. Okay, so here's how we detect a memory leak. We allocate, well, we call a function which returns a pointer. Now we own the pointer, and oops, we don't do anything with it. It's live on exit, so that's a memory leak. Now, there's an error in this slide. It should say @live in front of the void star. But malloc and free are not special to the language. And what this means is you can still write your custom allocators and deallocators, and they'll work just fine. You don't have to, it doesn't only just work with malloc and free. They're not special. Here's another type of memory leak. We're allocating, well, first we're returning a pointer to P, and then we're not doing anything with it, but overwriting it with another owned pointer. Well, overwriting an owning pointer with another owned pointer is clearly an error because it means that the first one leaks. So it's a leak. This is caught at compile time as an overwrite of a live pointer. Double free. Here we create an owner P and then we transfer P to the free function. Well, once we transfer it, it has an undefined or an invalid value and it won't let you transfer it again. So again, we have a compile time error here. Use after free. We create an owning variable, we assign through it, which is good. We transfer it to P, which is good. And then we try to use the variable again, and that does not work. It fails at compile time because P has an invalid value, because as soon as it was transferred to free, now it no longer has a valid value. Okay, now let's say we borrow a pointer. We borrow from P, and we borrow it by assigning it to a pointer marked with scope, and it will not allow us to pass it to free because you cannot transfer a borrowed pointer, or you cannot turn it into an owner, and you get a further error then because P is left dangling at the end of the function. Constant pointers. Well, remember I said you can have many constant pointers. So we can take C1 and we can borrow it as a constant reference to P. We can make another constant pointer. That's just fine. That's not an error. We can read from C1. We can read from C2. We'll note that C1, oops, I forgot to use my pointer. C1 is still live here. But suddenly we start using P. Once we start using P, now C1 and C2 become invalid, and we get errors when we try to read from C1 and C2 because those are now valid. No, those are no longer valid. And then we free P, disposing of it, transferring its ownership to P, which does whatever P does with it. Calling functions. Remember I talked about the reference counting problem of passing more than one mutable reference or mutable and a const reference to a function. The first one, the references passed are constant, so that works. The second one, one's constant and the other's mutable, that does not compile. That eliminates that problem with the reference counted object. And of course, this slide explains that in a little more detail. Global variables have a problem. It's because multiple functions can access global variables, and it's not clear from the function signature which global variables might be referenced by a function. The most straightforward thing to do is live functions cannot access mutable global variables at all. They have to come in through the front door, which means they have to come in through the parameter list. Now, it turns out that this is congruent with good programming practice anyway. So shame on you if you're having your functions read global variables. You should pass them through the parameter list as arguments. And I know I've been very, very guilty of using global variables, and I've been gradually fixing my code to pass all globals through the front door. D is full of other different kinds of pointer types. We have, reference types, out parameters, class references, implicit this references, pointers wrapped in structs, so-called smart pointers, dynamic arrays or slices, delegates, which point to context stack frames, and associative arrays. And they're all basically different kinds of pointers, but the flow analysis treats them all like pointers. So when you see a complex data structure with pointers in it, always think of them as being just like pointers, and that's how the flow analysis is going to work on them. With this is a bit controversial. GC allocated pointers are not special. They're handled just like any other pointer. There's no distinction. So if you're using GC pointers in an @live function, it's going to do the the ownership borrowing checking on it. Some people in the D community think that GC pointers should have a distinct type. I think that would increase the complexity, so it's not really worth it. Anyhow, if you're using GC allocated pointers, why are you using @live anyway? @live is for, you don't need it if you're using GC allocated pointers. Okay, the ownership borrowing checking begins and ends at the function interface, which means that if you have an @live function and it's calling non-@live functions, it expects the non-@live functions to conform to the interface. In other languages, you'll see this as being able to call unsafe functions. It's a similar idea here. But the consequence of this is you can take an existing program and incrementally add @live function capability. And in fact, that's true for all the memory corruption checking stuff in D. You can add them incrementally, which means you can add it when you feel like it, when you can add it when you're upgrading a certain section of code, and you can do it without disturbing the rest of the program. What you don't have to do is take your program, throw it away, not only rewrite it from scratch, but re-engineer it from scratch. You do not have to do that with D. You can add all this stuff incrementally to your existing code base. Exception handling. The trouble with exceptions is it causes too many complicated edges in the control flow. And in fact, one thing that is not much appreciated is most data flow optimizing compilers give up with exceptions. If it sees a bunch of try blocks in your code, it's going to cripple the optimizer. And this is a hidden cost of doing exceptions. The idea that exceptions are zero cost is basically a fraud. One of my problems with reference counting code is that in order to properly run the destructor, you have to put running the destructor in an exception handler. And this kind of really cripples the efficiency of reference counted objects, which is why everybody likes to pass them by reference, which doesn't get the reference count incremented. But when you pass them by reference, then that exposes you to the more than one reference to one function and one of them destroying the other problem. So this is why @live functions are no throw. You're not allowed to throw exceptions from them. And it's also why in the last few years I've started more and more to gravitate towards trying to make no throw the default in the language rather than throwing being the default. And also I've been more and more trying to write my algorithms so that they do not need exception handling to work properly. And I recommend that as general practice going forward. Okay, implementation. A lot of people told me it doesn't work well, or it cannot work. Now you can try it for yourself. It's available in prototype form in the latest decompilers. So you can try it, find bugs with it, and decide for yourself if it works or not. Okay, this all builds on existing successful safety mechanisms in D. Mechanically guaranteed memory safety is really the only way forward because it's just too difficult to review. It does not break existing code. It can be added incrementally. And I'll also say it does not break your existing algorithms either. So some handy references. And that's it. Thanks for listening, and any questions? And how do I break out of full screen mode?
Just hit the stop sharing.
Stop sharing. Well, if it's full screen, it doesn't have a stop sharing thing. Oh, that little X there?
Yeah, the little X where you screen share.
Wonderful. Okay. I'm not getting any audio.
Okay, I got a question for you, or actually more of a statement or an argument. You were talking about the ref counted pointers when you go to share them and one guy forgets to add it or release. Most smart systems that used a ref counted thing used a shared pointer that it would automatically internally maintain the an add ref and release on assignment, and it couldn't be called from outside of that. So if you assigned it to a variable, that variable was really a type of a smart pointer that would do the add ref for you. So you wouldn't have your problem of orphaning counts and forgetting to add them or letting something die.
Well, you are correct, but every time you add a count, you have to have a corresponding decrement account.
Well, right.
And every time you have a decrement account, you have to put it in an exception handler.
Right. Okay. So if you do this within a smart pointer object, the object itself is decremented when it goes through the destructor and goes out of scope.
Right.
No matter what way it goes out of scope, either the exception or the return, at the end it decrements its ref count.
You're absolutely right. But whenever it decrements the account, that destructor has to be put in an exception handler.
No, well, you put it in the object. It's the smart pointer itself, and the exception destroys the object.
Yeah, it destroys the object through the destructor in the shared pointer, and that destructor gets called via an exception handler.
Yes.
Okay, that's where the trouble comes from, because it's expensive to do that. So what happens is people pass shared pointers around by reference, which means they bypass the increment and decrement mechanism. And that's where this trouble comes in, is when you pass it by reference. So there's a powerful incentive for people to pass it by reference for efficiency reasons, but then you're wide open to this other problem.
A smart pointer is the same footprint as a reference because it is effectively a pointer that's got semantics around it. And
that's
so there's no reason to try and do a cheat on that. And if you did try and pass it by reference, you could actually put a reference operator on your smart pointer that blocked you from getting a reference to it.
Yes, you can do that, and then you lose the efficiency.
Yeah. Well,
but this whole thing is about people inevitably trying to optimize their use of shared pointers.
Well, that's like saying seatbelts don't save lives if you don't put them on. And it's because people aren't going to put them on. So
well, if your car goes faster without your seatbelts, you can bet people won't put them on.
More people die since we've added safety features to cars because they do go faster and are more dangerous.
All right.
Yeah.
But I actually think we're in agreement.
Yeah.
We're technically in agreement. Now, our disagreement is whether people are likely to pass shared pointers by refs. I say they are. You say they aren't. Well, okay. We can both be correct, actually. I know I would, simply for efficiency reasons. I want things to go as fast as possible, and exception handling and stack unwinding code is slow.
It looks like Travis popped in with a question, or maybe he's just unmuting his video. I'll exit out here and let Travis have his question.
All right.
Oh,
I didn't have a question.
Good question.
Oh, we scared him away. So, and what is Goofy's job in your company there?
Well, when I go to bed, Goofy takes over and adds bugs to all my code.
Oh.
Every time I have bugs in my code, I blame my partner.
Instead of a rubber duck, you have Goofy.
Hey, Ali, glad to see you.
Okay, do we have any more questions? Okay, well, I guess if we're out of questions, we can go ahead and stop the video. And if folks want to hang out and chat some more, feel free. The room stays open until the last person, excuse me, until the last person actually leaves. So you guys are more than welcome to just hang out and chat or disappear if you would like. Thanks again, Walter. And yep, you can send me your slides. I'll get those posted as well.
Thank you.
I stopped recording.
Cool, thanks. Hey, Peter.